All right, I wanted to add one more piece to our knowledge of how to deal with binary numbers in computers, and that is how to deal with minus signs. So if we're dealing with just base 2, we could imagine doing something like, okay, well, if 1, 1 is the number 3, then there's no reason we can't write minus 1, 1 to be like the number minus 3, right? But the whole point of this is we want to be able to represent these numbers with literally only ones and zeros in such a way that they can be stored on a computer. So one idea that you could imagine is, well, why don't we just have a little other 1 or 0 that says whether we need a minus sign there or not. That kind of works sometimes, but there is one more clever way to do this, and that's what I want to talk about. So that's this is called 2's complement. Numbers. So the numbers we've talked about so far being stored in like binary digits are unsigned integers, meaning that they don't have a sign. They're always assumed to be positive. Our counters go from 0 to 15. Our 4-bit counters go from 0 to 15 and then roll over to 0. So the idea of 2's complement is that this is a system for representing negative numbers that preserves some very convenient properties of integers. So in other words, if we have, for example, a 4-bit number. So normally, the way these 4 bits would be interpreted is, 0, 0, 0, 0 is 0. 0, 0, 0, 1 is 1, and the highest number we can have is 1, 1, 1, 1, which is 15, right? So as we count up, as the counter counts upward, we go up to 15. So this is an unsigned integer. So the idea of a 2's complement number is that we can store the negative number in such a way that addition of these numbers is still preserved. So let me explain what it is, and then I'll show you how it works. So here's the 2's complement version of what I just wrote. So 0, 0, 0, 0 is still 0. 0, 0, 0, 1 is still 1. And this is still true up to 0, 1, 1, 1, which is still 7. But something changes. 1, 1, 1, 1 is actually negative 1. 1, 1, 1, 0 is negative 2. And so counting down from the other direction, we end up at 1, 0, 0, 0, which is negative 8. Okay, so in other words, we can get the minus sign equals, getting a minus sign is the same as inverting all the digits and add 1. So if I want to know what minus 7 is, to get minus 7, I invert all the digits, so that would be 1, 0, 0, 0, right? 1, 0, 0, 0, and then add 1. 1, 0, 0, 1. So that is what minus 7 would be, and you can see how it would fit into this pattern. Now, instead of this, there are still 16 different states of this number. It's just instead of these numbers representing 0 to 15, they represent minus 8 to 7, which, sometimes we want negative numbers, so that's a useful thing to be able to do. Okay, so why the heck would we want to do it like this? Well, let me show you. Let's say I want to add together 2 numbers where one of them is negative. So let's say I want to subtract, let's do something simple. 6 minus 2, right? This is what we can do in our head. So of course, 6 minus 2 is the same as 6 plus negative 2. And we know that 6 in this system is going to be 0, 1, 1, 0. So this is 6 in base 10. And now if I add -2 to this, -2, like we just wrote down a moment ago, was 1, 1, 1, 0. And I guess I really shouldn't put that this is in base 10 because this is 2's complement. This is not a mathy thing. This is a computer science thing now. This is a digital circuits thing. And we've moved away from the Boolean mathy part of this. So if we have an adder, a 4-bit adder that adds these numbers together, 0 plus 0 is 0, 1 plus 1 is 2, so that's carry the 1. 1 plus 1 plus 1 is 3, and 1 plus 1 is 2, which is 1, 0, but we're just going to throw the carried 1 away. We only have 4 bits, so it's only going to fit into, our output is only going to fit into these 4 bits. We're not ending up with any extra digits out there. So 0, 1, 0, 0, of course, is 4. So that's what I mean when I say this. The 2's complement math, the way this is arranged is that adding numbers or subtracting numbers works just the same as you would expect. If you add a number to its negative value just using the regular adder, you end up with the correct result. So that's why the 2's complement is so convenient and is preferred for this kind of system.